All right, guys, those of you cramming for this AP exam that is tomorrow, here is yet another example of what people are asking in regards to extra practice, okay? So we have this FRQ, it's AB2, and again, this is different from the ones that I put out from before, and we're given this f of x graph. It says a portion of the graph of the twice differentiable function f is shown in the figure above. The areas of the regions bounded by the graph on the x-axis from -2 all the way to 6 are shown above. So this is like, this is 10 right here. This area is a positive 10. This is a positive 3. This is a positive 9. However, this one should be interpreted as a negative 5 because it is below the x-axis. So don't let them catch you with that negative mistake immediately. Please understand that below the x-axis is negative and above is positive if you're reading left to right, okay? So the last part says at x is equal to -2, the line tangent to the graph of f is shown along with its equation. And you see I already have it highlighted. And the function h is defined by the following function that you see there. Okay, so let me go ahead and take all of this off. And now we're going to go ahead and go straight to part A. Part A is saying let's integrate this f of 4 minus 2x in respect to x from -1 all the way to 2. Now, we can't simply just look at this graph and integrate from -1 to 2 because that's not the way it works. We can only do that if this was just saying f of x. But because it's not saying f of x, we already know we have a u substitution composite function, if you will, going on here. So we're going to say u is 4 minus 2x. Therefore, du, its differential, is -2 dx. And the rewrite for this integrand is going to change to a -1. Remember, it's going to change to in respect to u. And now it's going to be f of what we established as being u. So it's f of u du. And now we have to change our bounds. We have to change this -1. We'll put it in there where x is at. So 4 plus 2 is going to be a new lower limit of integration of 6. And then now when we plug in our other piece 2 right here, it's going to be from 6 to 0. Okay, so we have from 6 to 0. And we know we typically integrate left to right, which is a lower x value to a higher x value. So one of our rules of integration, or our laws of integration, if you will, is we're going to flip this to say from low to high. So from 0 to 6, f of u du. And because we did that, because we flipped those two, we have to account for it with a negative. Well, we're already going to multiply with this -1/2, so it's going to be a negative times a negative becomes a positive 1/2. Okay, so now I'm just going to integrate what is the area underneath this graph, which now we can look at as quote unquote f of x, and it's going to be from 0 all the way to 6. So from 0 all the way to 6, we're going to look at what is the area underneath the curve, if you will. Okay, that's going to show what's highlighted here in blue. Well, just like before, I said this is a positive 3. This is a -5 because it's below the x-axis. And then this last piece is going to be a positive 9. So we'll have 12 minus 5 is going to be that 7. And then we'll have 7/2 because we're going to multiply by this 1/2. So our answer for this one is going to be 7/2. Okay, let's go to part B. Part B is looking at possible. Immediately at this point in the game, I'm looking at limits and I'm thinking L'Hopital's rule most likely. Okay, so we just have to verify and make sure that that is in fact correct. So is the top function continuous, and what is it equal to whenever I plug in this x value of 2? Okay, so first of all, let's first see, is h continuous? Well, it does say that h is continuous, or at least it shows that h is defined by h of x as the following, okay? And h of x is composed of area underneath the curve of f of x, if you will. And we already know that f of x is twice differentiable. That means it is continuous as well, 2 levels, if you will. So if f is continuous, then h is continuous. But we have to mention that. We're going to say h of 3x minus 7 is continuous. Okay, the next part of this is we're going to say what is the limit just of the numerator as x is approaching 2? So what is the limit of just this numerator piece as x is approaching 2? Well, if I'm going to put 2 in here, it's going to say h of 6 minus 7. Okay, so what is h of 6? Well, here is our x, or our h of x, that is, and we're going to say h of x is equal to 0 to, in this case, it's going to be 6, because this is our value that we're trying to find. What is h of 6? Well, let me make some room up here and do it up here. H of 6 is going to equal this integral from 0, in this case, 6. So what is the area underneath the curve of f of t, which is shown up here, between 0 and now 6? Okay, we already know that that was that, I believe that this, what is it, 7? Yeah, 7. So it's a positive 7. So 7 minus 7 is equal to 0. Again, that h of 6 we got from that 7. In part A, we multiplied to get 7/2, but nonetheless, just for part B, we're going to say 7 minus 7 is equal to 0. So the numerator is equal to 0. Now, let's look at the denominator, okay? So the denominator is this sine of pi x, and we know sine is continuous. But we have to mention it for L'Hopital's rule, so we're going to say is continuous. And then we're also going to show that the limit as x approaches 2, which in this case will be sine of 2 pi, is also equal to 0. So please, 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 please do not say that this is equal to 0 over 0. If you show this equal sign, they're going to say, no, you don't understand L'Hopital's rule. It's not equivalent to 0 over 0. It is simply saying the numerator is continuous and equal to 0. The denominator is continuous and equal to 0, because it's referencing and saying that you have, or you're given, we'll say we have a 0 over 0 indeterminate form. It doesn't equal 0 over 0. It results as a 0 over 0 indeterminate form. So please do not put that equal sign. And now we can go ahead and use L'Hopital's rule. So we're going to say per L'Hopital's, if you will. So per L'Hopital's rule, so we're going to take the derivative of the top independently from the bottom. No quotient rule is going on right here. But we are going to take the derivative of the top and get h prime of 3x times the derivative of that inside piece, which is 3. We know the 7 zeros out. And on the bottom, the derivative of sine is cosine of the stuff, but then multiplied by the derivative of that inside piece. There's chain rule going on. This is the derivative, the first derivative of the top and the bottom. Our moment that we're evaluating it at is still 2. So now when I plug that in, let's see if we still get this 0 over 0 indeterminate form, which means we'll have to do this all over again, or do we get a quantitative answer? Okay, so let's go ahead and plug this in. So 2 plugged in here gives me h prime of 6. Okay, h prime. I knew what h of x was, but I don't know h prime without needing to use per second fundamental theorem. So we're going to say per second fundamental theorem of calculus, we're going to take the derivative of the left, which is h prime, and the derivative of the right, which is just f of x. So when we're looking for h prime at 6, it's the same as f of 6. This is an f graph, so f of 6 is 8. It's that y value. So we're going to say 8 times 3 is going to be a 24, okay? So far, not 0. So maybe we don't have a 0 over 0 form anymore, and we're going to have our answer here shortly. So now we're going to plug in 2 for the denominator piece right here. Cosine of 2 pi is what is the x value at 2 pi radians? That's going to be 1. Multiplied with pi, you get 24 over pi. So 24 over pi is going to be the answer. Please don't forget to mention per second fundamental theorem and also reference that L'Hopital's rule, but do in fact show the pieces that are required and mention that it is a 0 over 0 indeterminate form. And you should be good. A lot of people are struggling with L'Hopital's rule and tend to, because there's so much involved as far as justification and correct reasoning, but please make sure that you are careful with all those pieces. Let's go to part C. It says find any x values where h of x has a relative max. Already I'm thinking, when does h prime of x change signs from a positive to a negative? That will show me per first derivative test. Okay, so let me go ahead and write that over here. Per first derivative test, that I can find where that is occurring if I just analyze this criteria right here. Okay, so give the reason. We're going to start with per first derivative test, and now let's find h prime of x. Well, per second fundamental theorem, we're going to reference, again, like we did in part B, that h prime of x is equal to f of x. Okay, so this right here is saying h prime changing from positive to negative is the same per second fundamental theorem as f of x changed from positive to negative. So on our graph of f of x, we want to analyze, when does this graph change from a positive to a negative? Well, it would change from a positive to a negative, guys, right here at 2. Okay, so we're going to say, actually, let me change that up just real quick. H prime of x has a relative max. Yep, it's going to only do it at 2. That is correct. So we're going to say that h prime, or h of x, has a relative maximum at, it doesn't want to know what is the y value, it wants to know where is it at. X is equal to 2, because we're going to say f of x changes from positive to negative. And again, it still has the mention of the second fundamental theorem to be able to use f of x instead of h prime, and also first derivative test to show that it was changing from a positive to a negative. Now, the AP exam loves for you to also show all critical points so that you know you're testing all critical points. Okay, so that means the critical points will be when h prime is equal to 0. Well, we know h prime is the same as f of x, so it's the same as when f of x is equal to 0. So the ones that you want to list out per se is, when is f of x equal to 0? Right here, and right here, which is going to be 0, 2, and 4. So you're basically telling the AP reader that I'm thinking that f of x is equal to 0, which is the same as h prime, at x is equal to 0, 2, and 4. So at least that you're telling them these are possible critical points. These are possible points where this relative max could occur. Okay, for this one particularly, I would suggest listing them out, but nonetheless still use what you know as far as you analyzing just that positive to negative change to show that your only one's going to happen at x is equal to 2. Okay, so now let's go to part D. It says consider the curve. Okay, all of that is equal to h of x. Find the slope of the line tangent to the curve at 6, 1. Okay, so we're going to find h of x is the curve per se, and we're trying to find h prime at this point. Okay, that means x is 6 and y is 1. Well, implicit differentiation is screaming at us right now. Okay, so if we did 2y, then implicit differentiation says dy dx. And we have a 2 with this product rule between the first times the derivative of the second plus the second times the derivative of x, which is just an understood 1. So I'm just going to write it just as y. Okay. And then we have minus 1 because we're in respect to x. Our input variable, okay, is x. So that way I know that this is going to be a minus 1 and not a minus dx is equal to h prime of x. Okay, and I know this is kind of weird because you're used to seeing like just dy's everywhere and not this h prime of x. So this is a clever question because we're looking at the input of 6 for all of our x values. We're looking at the output value of 1 for all of my y values. And we're trying to find what is dy dx. Okay, So when we get our dy dx all by itself, it's basically saying what is the dy dx at this value when x is 6 and y is a positive 1. That's what it's really looking at. So you could even note it if you want as that point 6, 1, similar to like calculator notation. Okay, so we know we're going to have to plug in a 6 here. So let me go ahead and write h prime of 6. We know we're going to plug in a 6 here. So I'm going to go ahead and write 6. And then everywhere where we had a y, I'm going to go ahead and write 1. So there's a 1. And yes, this could be 1, but I don't want you thinking 21. It's 2 times 1. So this is just going to be 2. Okay, so now our goal is to get this dy dx all by itself, okay? So let me go ahead and distribute some stuff. Okay, so right here we'll have a 12 dy dx plus 2. Careful with that distribution. 2 dy dx minus 1 is equal to h prime of 6. Well, what is h prime of 6? We know from other parts that second fundamental theorem, so I'm going to mention it again because I'm using it again in this piece, that h prime of x is f of x. Okay, so therefore h prime of 6 is f of 6. Well, f of 6 is going to be what is the y value on this f of x graph at 6? Well, it's going to be 8. Okay, so f of 6 is 8. So we're going to go ahead and put that h prime of 6 all resulted as 8. Very, very, very clever question. Now we're just trying to get dy dx all by itself. So I'm going to go ahead and group all of my pieces together. So I have a 2 minus 1 is 1. So when I move it over to the right side, I'm going to have 7 left over. Put scratch work over here. And then I'll have this right here, which is like a dy dx. And then it's like this 2 plus 12, if you will. Or you could have actually add them up together and say 14. So 14 dy dx. Okay, and this is equal to that 7 on the right side. So if you wanted to know what is dy dx all by itself, well, it's 7/14, otherwise 1/2. So my answer for part D is going to result as 1/2. Very, very clever question, especially the way he used this h prime of x here on the right side with our at moment of 6, 1. Okay, very, very clever the way this question was asked. Okay, let's go to part E, and then we are done. E is asking, let k of x be this function, just find the derivative at 6. So if I derive the left side, that's easy, k prime. And now there's a product rule going on. The first times the derivative of the second, which we know is going to be 2e to the 2x, plus the second times the derivative of the first, which is just going to be h prime of x. And that's just basic product rule differentiation. Okay, so now we're going to plug in our at moment, if you will, of 6 everywhere we see an x. Okay, so we have h of 6, okay, and it's going to be times 2e to the 12th plus e to the 12th, and then now we have h prime at 6. Okay, remember h prime at 6 was the same like we did in the past problem, was the same as f of 6, which meant that that was the 8 here. So I'm going to go ahead and put 8 here. So h of 6, let's find h of 6, because we got to make sure that we are not using this as the same. One is h and one is h prime. Okay, so let me go ahead and write this out. So h of 6 is, if we were to use our original integral up here, whoops, remember, it's the area that we got from up here. So the area from 0 to 6 was that 7 from before. That's going to be 7. So 7 times this 2 right here is going to become a 14. So 14e to the 12th plus 8e to the 12th is going to finally result as k prime of 6 is equal to 22e to the 12th. There you go, guys. Hope the extra practice helps.